So in the meantime, we've been talking about Gibbs free energy, enthalpy, and entropy, and they have this relationship. If you want to know if a reaction is spontaneous, you evaluate G, delta G, Gibbs free energy, and if it's negative, voila, it's spontaneous as written. And so we talked about how could you get a negative delta G, and remember, spontaneity favors the dispersion of two things, the dispersion of energy, so the enthalpy term takes care of that, and the dispersion of matter, and the entropy term takes care of that. So just to kind of remind you. So there's this relationship between those three variables. Okay, and then I think we left on this slide. So you can get to the Gibbs free energy of a reaction if you know the change in enthalpy of the reaction and the change in entropy of the reaction. Remember that this T is the Kelvin temperature. Or you can get to the Gibbs free energy for the reaction if you know the Gibbs free energy of formation of all of the reactants and the products. Okay, so actually now we get to work a problem. So when you look up on a table, a lot of times for the thermodynamic values for a compound, there'll be three columns. There'll be this Gibbs free energy of formation, the standard molar enthalpy of formation, the delta H, and the entropy. A lot of times be those three columns. Okay. The Gibbs free energy of formation of an element, if it's in its standard state at standard conditions, is 0. That can be helpful. Okay, I know we had this kind of the entropy of a crystalline substance at absolute 0 is also 0. That's not very practical. But remember, standard state at standard conditions. So standard state, that would be what? 25 degrees Celsius, 1 bar, and 1 molar if it's an aqueous solution. So that's kind of nice. If it is an element in its normal conditions, so like at 25 Celsius, 1 bar pressure, of course, nitrogen, we'll pick on nitrogen, is a diatomic element in its gaseous state. Okay? So the Gibbs free energy formation of that would be 0. Okay. Standard molar enthalpies of formation. Oh, see, I picked on nitrogen. So here we go. You know, at standard state, in its standard condition, which is a gas, it's 0. Okay, so these are some standard molar enthalpies of formations of some compounds, or some substances. Okay, so let's do a problem where we're burning methane, combustion of methane to form carbon dioxide and water. Notice that the physical phase is important because that, when you look it up on a table, needs to match up with the thing you're picking off of the table. So we're supposed to calculate the change in enthalpy of the reaction, the change in entropy of the reaction, and the Gibbs free energy for the reaction. So when we come up with the delta H here in a minute, the change in enthalpy, we'll be able to know if it's endo or exothermic. So I'll just remind you that if, let's see, endothermic, that would be what? A positive delta H. Exothermic would be a negative delta H. And remember, exothermic is the dispersion of energy, and actually that favors spontaneity. Spunky spont. Okay, here in a minute we're going to knock out the change in entropy for this reaction. And so we've been talking about if something becomes more ordered, then actually that is going to be what? A negative. If it's more ordered, that's going to be a negative delta S. More disordered, it's going to be positive delta S. And of course, this whole disordered, that favors spontaneity. Spont. Okay. And then we're going to come up with the change in Gibbs free energy for the reaction. and we will be able to know is it's written, is it spontaneous or not. And so just to kind of remind you, when you're doing Gibbs free energy of the reaction, checking for spontaneity, what you're doing is you're looking for it to be negative if it's going to be spontaneous. So this table kind of summarizes what I just kind of imposed on the previous slide. Delta H's, endothermic, that's not the dispersion of matter is positive, exothermic's negative. Change in entropy, positive. Change in entropy means it's becoming more disordered, dispersion of matter. Negative entropy change, it's becoming more ordered, doesn't favor spontaneity. Gibbs free energy for a reaction, delta G. If it's positive, it's not going to be spontaneous. If it's negative, it will be spontaneous. So these are the three thermodynamic columns associated with these, the reactants and the products. One is that it's always products, the summation of the products, okay? From that, you subtract the summation of the reactants. It's really easy to make a mistake here.
And you just get all that from the table?
Yep, and that's all going to be from the table. The problems are kind of a little bit different, like your homework, but we'll kind of, this one we're just going to get them from the table.
Okay.
So if we look up for the two products, the carbon dioxide in the water, remember we need the stoichiometric, to bring in the stoichiometry, that's the lowercase a here, or sorry, lowercase b, no, a. So the coefficient in front of CO2 is 1, so it's 1 mole of CO2 times its standard molar enthalpy of formation, negative 393.5 kilojoules per mole, plus 2 moles of H2O, because that's the coefficient in front of the water, the product side, times its standard molar enthalpy of formation, negative 285.8 kilojoules per mole of H2O. So for the products, you're looking at an ending value of enthalpy of negative 965.1 kilojoules. Then we do a similar thing for the reactants, methane and oxygen. So the coefficient in front of the methane is 1, so 1 mole of CH4. And then the second term is from the table. That's the standard molar enthalpy formation for methane, negative 74.8.
I was going to say, is that an error?
What's that?
Is that an error?
Yeah.
Okay.
Negative 74.8.0. What was that?
It's just 74.8. So
Okay, thanks.
Extra.
Very good. 74.8 kilojoules per mole of methane, plus 2, because the stoichiometric coefficient from the O2 is 2, so 2 moles of O2. And that is in its standard state under standard conditions, so the standard molar enthalpy of formation is 0 kilojoules per mole of O2. So then the next thing, all we got to do is take this first number and from it subtract this negative 74.8, recognizing that when you subtract a negative number, it's like adding a positive number. So for the reaction, on the product side, we have negative 961.1 kilojoules minus, on the reactant side, a negative 74.8 kilojoules. And I get, and we're round according to decimals, remember, I get the standard molar enthalpy change of the reaction. Sorry, that doesn't make sense, molar. The enthalpy change for the reaction is negative 890.3 kilojoules for that balanced equation. Negative 890.3 kilojoules, yep. All right, so that's one of 3. Oh, and so now we can answer this question. Since it's negative, that means it's exothermic, that's the dispersion of energy. Okay, it's exothermic, so that would favor spontaneity. Now we move on to the entropy term, and I do a similar thing. We start with the product side, and so from the table we look up the entropy, the molar entropy for CO2. It's 213.7 joules. Now, notice these energy units are joules, not kilojoules.
Yeah, I was gonna ask, do you have to convert them?
Yes, will have to convert them. Yep. So that's the value for CO2. The value for H2O is 69.9 joules per mole Kelvin, and we have 2 moles in the balanced equation. So then on the product side, we have an entropy of positive 353.5 joules per Kelvin. Yeah, that's one thing to the kilojoules and joules. This is in joules, the other one's in kilojoules. So then we look at the reactant side. The 2 reactants, the methane, 1 mole of methane. So 1 mole of CH4 times the entropy, molar entropy, 186.3 joules per mole Kelvin. Plus the term for the oxygen, there were 2 moles of O2. And from the table for O2, it's 205.1 joules per mole Kelvin. So on the reactant side, we have a positive 596.5 joules per Kelvin. And so then we're going to have to take the top number and from it subtract the bottom number to get your change in entropy. Delta S of the reaction is that 353.5 joules per Kelvin minus 596.5 joules per Kelvin. So our change in entropy is negative 243.0 joules per Kelvin. So one of the things we've been wrestling with is if you have a negative change in entropy, that means are you creating or order or creating disorder?
Shouldn't it be more ordered?
Right, we're creating
So it
order
doesn't
here.
favor spontaneity.
That's right, this does not favor spontaneity. Very good. So we can answer the second question. Since it's negative, the reaction is creating order. Does not favor spontaneity. So we could go back and use the column for Gibbs free energy and do a similar thing, but instead we're going to use this one. So there's 2 ways to get Gibbs free energy. And since we already have the enthalpy change of the reaction and the entropy change of the reaction, this is how we're going to do it. We should get the same value the other way too. One of the things, remember I told you, don't let this throw you off. You're going to need a T, the capital T is the Kelvin temperature next to the delta S. As long as you have that little circle there, that's 25 Celsius, exactly. 25 plus 273 is 298.15 Kelvin. So it looks like in my notes, I'm just reminding us, earlier we came up with the delta H of the reaction is negative 890.3 kilojoules. And we said that favored spontaneity, that's exothermic. The change in entropy term we just came up with as negative 243.0 joules, not kilojoules, joules per Kelvin. And we said that disfavors spontaneity. So here's the little not part. We need an absolute temperature. And like you said, it's 25 Celsius. But we need it on the Kelvin scale. So 25 plus 273, actually 25.0 plus 273.15. is 298.2. If you went with 25 plus 273, and it's just 298, I think you'd be fine too. So let's go ahead and knock this out. Oh, before we knock it out, we got to fix, because our energy units are not the same, are they? Oops. And it looks like we're just going to fix them as we go. So you recognize this first term is your enthalpy, so negative 890.3 kilojoules, minus the temperature, the absolute temperature, that 298 or 298.2 Kelvin. Now we need the delta S. So just go ahead and put in your delta S is negative 243.0 joules per Kelvin. Notice the cool thing about this is units of Kelvin are going to cancel, okay, from our T term. But we need to introduce something, so we're adding apples to apples. And so here's where we fix our joules into kilojoules. So now we have basically a kilojoule and a kilojoule, and we're going to add them together. So when you do this correctly, rounding it to 1 decimal, you'll get the Gibbs free energy, change in Gibbs free energy for this reaction is negative 817.9 kilojoules. It is spontaneous. Very good. Not only is it spontaneous, but since the delta S term fought it, we say it's driven by the delta H term. So it's what we say enthalpy driven. So since it's negative, delta G is negative, like you said, the reaction is spontaneous. And like I said, it's enthalpy driven. Because the enthalpy term was the one that wanted spontaneity.
Now, if it was driven by both, what you just wouldn't say.
Right. If both of them favor, then you just say it's going to be spontaneous.
So earlier when we did the first, like the delta H, it was with moles, just moles. Is that because it was just in K or kilojoules? Because on the second part we just did moles per Kelvin.
Let's see.
So I didn't know if it was just because it was in kilojoules and that is just in joules.
I think the per Kelvin comes in, entropy is always going to have that temperature with it, and enthalpy does not.
Okay. Okay.
But yes. Okay, let's do another one. But now this isn't a chemical reaction. If you're like me, sometimes I'll do chemistry problems like, what? And if you look, the kicker is this, the physical phase. Okay, so picture's worth 1,000 words. All we're doing basically is dissolving ammonium nitrate. So it's not a chemical reaction, it's a process. There would be 2 different thermodynamic values for the solid ammonium nitrate versus the ammonium nitrate that's dissolved in water. But remember, I've been telling you, and actually we're going to hit this on this week. Remember that standard conditions for aqueous solutions are 1 molar. We won't need that today, but so it's a 1 molar solution of ammonium nitrate with that given thermodynamic values, set of values. So let's do a similar thing. We're going to come up with enthalpy change, delta H. And if it's positive, we know it's endothermic. If it's negative, it's exothermic, favors spontaneity. We're going to come up with an entropy term, delta S, for this process. And if delta S is positive, if delta S is negative, it's becoming more ordered. If delta S is positive, it's becoming more disordered, and it favors spontaneity. And then like we did with the combustion problem, we can come up with delta G for the process, the Gibbs free energy associated with this dissolving process. And if it's negative, then it's spontaneous. If it's positive, it's actually spontaneous the other way.
Shouldn't it be spontaneous because we're going from a solid to a liquid, which...
Just because by inspection? Yeah. exactly.
I was gonna ask you.
Yep, very good. Just by inspection. And now we're going to prove that to ourselves with the numbers. Yep. Okay. So like I said, you look up these ammonium nitrate, and in its solid state, okay, it's got different values for enthalpy of formation, the entropy, and the Gibbs free energy of formation. Now this one we're going to do a little bit different, okay? It's going to be a little bit kind of more cut and dried. See if you guys buy this. Okay, so the delta H is always products minus reactants. Okay, so product minus reactant, PR. Of course, the products we said was the AQ, and the reactant we said was the solid. Okay, so you can kind of double check that if you want. Product for the, see, my eyes go buggy, don't they? I'm like, goodness gracious. Yep, there's the AQ, there's the negative 339 minus 9 kilojoules. From that we subtract 365.6 kilojoules. So this is where, if you're like me, this is, if anything's going to get us, it's going to be that, minus a negative. Arr! Okay. So we do come up with a positive change in enthalpy. I mean, it's very doable, but, so what do you think?
So it's not spontaneous.
That does not favor spontaneity. That does not. Now, it doesn't mean it's not spontaneous, but the enthalpy term disfavors it. You're right. So we would call that endo or exothermic?
That'd be
Endothermic. Yep, endothermic. So we'll do a similar thing for the change in entropy. Okay. So here we're just looking at these values up here. We're going to take that 259.8 joules per Kelvin. Oh, and here, notice we're not doing the mole thing because it's a one mole. We're kind of, do you know what I'm saying?
Yeah.
Okay. And from that, we're going to subtract the 151.1 joules per Kelvin. So it's positive change in entropy.
So it's more ordered.
So it's positive delta S, so it's,
Disordered.
more disordered. Increasing,
Oh, I read it wrong.
decreasing order, increasing disorder. Yep, more disordered, yeah. So what do you think? Does that favor or disfavor spontaneity? It favors. Yeah, it will be S-driven if delta G, which it is going to be negative. That's right. You got it. So then instead of using, remember there's two ways to get at the change in Gibbs free energy. We're going to go ahead and just use this column here for this one, if that's okay with you. Okay, so using that last column, since it's kind of easy, we only have one reactant, one product. We take the Gibbs free energy formation of the aqueous ammonium nitrate negative 190.6 kilojoules, and from that we subtract the Gibbs free energy of the solid, which is negative 183.9 kilojoules. Again, we have a minus, we're subtracting a negative, so actually you end up with a negative 6.7 kilojoules, which you guys told me is spontaneous, exactly. It's spont. So then we say, like you said, we say that it is spontaneous, okay, but it's going to be driven by the entropy term. Is it an entropy-driven spontaneous reaction? Doesn't that just roll off the tip of your tongue?
delta H, correct?
Right.
Okay, and entropy is delta S?
Yes.
Okay.
And something. So I think we already found that.
And do we have to write that?
No.
I'm just gonna
Okay, so here's what I did with this assignment slide. And I have hints for all of these, but if you do 25, you don't have to do 25, but you get 10 extra credit points. And if you do all of 27, let me show you what 27 looks like. You would also get 10 extra credit points.
What if we did some of 27?
Probably 5. You can
Okay.
get part.
Okay.
I'll show
That's
you.
so
They're
good.
like Hess's Law ones, so.
Oh. Okay.
But the good thing about pulling yourself through 27 is it's going to help you possibly for the comprehensive final. So, so let's take a look at these.
You mean that problem I'm gonna skip?
What's that?
You mean that problem I'm gonna skip?
Yeah, right.
No way. Gotta tackle those fears.
Yeah, I gotta go for it.
So this one, it goes ahead, and sometimes you have to refer to the table, and sometimes they give it to you. So this one, they give it to you. Notice we're reacting NH3 with HCl to form NH4Cl. It looks like it's going to be a balanced equation because you need the stoichiometric coefficients. But it says from this determine delta S. Oh, yeah. Okay, so here, I'm like, well, why would you do that? My thing is, they don't give you a column for delta S. You're like, dude, how cruel is that? So you have to go roundabout. So here's, you do it stepwise. You knock out the delta H. You can do that. And then you knock out the delta G. Okay?
From there you can get delta S.
That's right. And then from there, you use that other equation
So
to
it's
get
like
delta
going
S.
just different.
It is kind of going backwards, kind of. And I don't know if I brought it, but remember I gave you that equation sheet for your final? And they're all up there, just kind of sitting. Yep. So that's how that one goes. And don't forget, so T, I have 25 Celsius, but don't let me throw you off. It's not going to be 25. It's going to
In the
be...
problem, it says 298, so do we have to show work for that? Like, converting it?
No.
Okay.
No, that's a good point. Nope, it gives it to you, so you can just plug it in there.
Just plug it in.
Okay. The next one looks like this. Okay. So this one you are going to have to go in the appendix, or you can just, in your notes, I think I have the tables. And you're going to have to find, and this is just for regular credit, right? You get to do this for every equation. So, yeah, it's not too bad. It's good practice. And then for this one's extra credit. Okay, it's still not too bad. Okay, so it gives you a reaction. 2 PCl3 reacts with 1 mole of O2 to form 2 moles of POCl3, and it gives you the like table information for the standard molar enthalpies of the reactants, and the product. Okay, that's what the purple circles are. So you can actually, I wonder if I said that. Oh, yeah. Okay, I was wrong. Those things that are circled aren't the enthalpies, they're the entropies. It says standard molar entropies. So those are the S's. Like for PCl3, the S is 311.8 joules per Kelvin. Okay, so you can get the change in entropy of the reaction. Okay, and then that delta H, that is the delta H of the reaction. So basically, you got this from step number 1. Delta H is given. Of course, the temperature is 298, and you can knock out the delta G. So it's not too bad either. A says, what is delta G? So that's A. And then B just says, if it's negative, it's spontaneous as written. Okay. So that one's optional. This is the same as 25, which is optional, 26 is not, okay? So again, they give the enthalpy of the reaction, they give the individual entropies, standard molar entropies. Don't you hate the enthalpy entropy thing? Okay, good, me too. So they give you the S's, they give the H for the reaction, the individual S's, so you do it the same way to get the Gibbs free energy. Okay. Then this one is optional. But like you said, if you, and there's 3, so A, B, and C, that is what it is. There's not that many. The reason, the 1 through 5 over there are your puzzle pieces, and I even tell you how to use your puzzle pieces. Okay? So it's like Hess's law, but instead of going for your heat of reaction, you are going for your Gibbs free energy of reaction. Okay, so 1 through 5 are your puzzle pieces. A is a reaction of interest, B is a reaction of interest, C is a reaction of interest. So I cheated, I went and looked at my answer key, so I didn't have to think too hard. Okay, so I tell you how do you get to manipulate them. So for instance, for A, okay, first off, once you manipulate them. So you manipulate the equations, okay, to get the equation of interest. And then whatever those delta G's are for your puzzle pieces, okay, then remember if you reverse it, you have to change the sign, okay. It's like their delta H's. If you take it all times 1/2, you have to take your delta G times 1/2, okay. And then once you have those puzzle pieces, basically you add up the delta G's to get your reaction of interest. Okay, and the answer's in the back of your book. What could go wrong there?
A lot.
So for A, you're going to use equations 5 and 4. So for A, you're going to reverse 5, take it times 1/2, plus just equation 4 as it is. For B, you're going to use equations 1, 2, and 3. And for the first one, you're going to take it times 2/3. For the second one, you're going to take it times 1/3. For the third one, you're going to reverse it and take it times 2/3. And for C, again, you're going to need 3 puzzle pieces. Take 1/2 of equation 2 plus 1/2 of equation 5. Reverse equation 3.
So basically that's going to be really easy because you just set it all up. So
Why would you tell her that?
well, no,
She'll never do that again.
It's very doable. No, it's very doable.
No, that's what I'm saying. Like,
Yeah.
There's no point not to do it because
Okay, we'll see that when we do it tomorrow.
Yeah, they're fun. But this was, the stuff
So
in
the-
red is kind of hard part, I think.
A, B, and C are kind of like prime, is how I take it.
They're
Kind of, in a way.
the
I'm
equations
confused
of
why they're-
interest. It's an equation
A
of
is
interest.
like
A is an
A.
equation of interest.
like
That's your
like
target.
If you did 3 parts of the problem,
Gets
you know,
really
like part
ugly
A,
almost.
part B,
Yeah.
part C, that's what that.
The primes would be the 1 through 5.
Okay.
And then how you manipulate it is kind of given here.
Yeah,
Like A is an equation of interest,
Yeah.
and for this one, you just need these 2 equations. And if you reverse and take 5, there's 5. See this one up here? If you reverse it and take it times 1/2, plus just 4 out of the box, if you add those 2 together, you're going to get A.
Oh.
Yeah.
Okay.
Now
I
you
thought it was
understand.
something completely different. I was like, oh my gosh.
Now do
Okay.
you understand what I said? That's going to be like,
Yeah,
Yeah.
really simple.
yeah.
Well, watch those beans. Okay, very good. So back to the slides. Okay. So we said the Gibbs free energy is a way to check for spontaneity. Okay. Another way to check for spontaneity is your K, your equilibrium constant. Okay. Oh, is this right? I don't remember this part. Okay. So I think we looked at this before. If it's right at equilibrium, if you're talking about a reaction that's right at equilibrium, the Gibbs free energy is 0. Okay. If it's negative, it's going this way. If it's positive, quite frankly, it's going the other way. Okay, but if it's right at 0, it's right at equilibrium. So if we go ahead and set delta G, Gibbs free energy, equal to 0, then we get this enthalpy is equal to the T times the change in entropy. So this is kind of a review. If it's negative, it's spontaneous. If it's 0, it's at equilibrium. If it's positive, it's basically going back to, from products back to reactants again. Well, like I started to kind of say, the rate law constant K, remember we talked about a reaction quotient Q. Q is a snapshot, okay? K is the equilibrium constant. So that might ring some bells. So actually we're going to see that Q, we said, if Q was equal to K, if your snapshot was equal to your equilibrium constant, the thing was at equilibrium. And actually that corresponds to delta G being equal to 0. I'm setting up a link between Q and G. Earlier, we said that if your snapshot was too small, if your Q reaction quotient is too small relative to your equilibrium constant, then that means you don't have enough, remember products are in the top, you don't have enough products, so the darn thing's going to have to form more products. So actually, that's spontaneous. That's this way to form products if Q is less than K. Okay? And that actually corresponds to a negative Gibbs free energy. So those two go together. The last scenario we said is if your reaction quotient, Q, was too big. If it's bigger than your equilibrium constant, then you have too many products, because products are always in the numerator. So if you have too many products, it's going to go back that way. Okay? So actually, that's a deal where that's non-spontaneous. That is a positive Gibbs free energy. Okay? So we definitely have, not between K and G so much, but between, I guess, K and G. But we definitely have this relationship with regard to spontaneity. And so it kind of enters into this sort of thing. Do you remember that is a proportionality symbol? So the Gibbs free energy, change in Gibbs free energy is proportional to the natural log of the reaction quotient Q over the equilibrium constant K. Well, we can replace that symbol with an equal sign if we introduce a constant. And it works out real well that the constant we're going to introduce is the ideal gas law constant. So blue box means, let's see if it's on here. Yep. Blue box means it's on here. Okay. There is, for the same reaction, this relationship between the equilibrium constant, K, and the Gibbs free energy for the reaction is related in this relation by this way. So let's do a problem where we use that equation, which you're going to have in your final. We use that to our benefit. So we're supposed to come up with the equilibrium constant K. And if you're like me, you're like, dude, equilibrium constants are for equilibria. That does not look like an equilibrium. It's like a one-way error to me. Well, we're going to kind of go see what that K is. So if we know the delta G, according to this relationship, if we know delta G, we can get to K. Because R is the ideal gas law constant, and T is the temperature. Okay? So here we go. Let's go from that Gibbs free energy to K. So rearranging the change in Gibbs free energy is equal to negative RT ln of K. Rearranging it to isolate K by itself. Now, not to mention that it's the natural log of K. We're going to fix that at the end. The natural log of K is equal to Gibbs free energy of the reaction divided by ideal gas law constant times the temperature, which again, it's 298, okay, and it's negative. So let's plug in let's plug in some numbers there. So the Gibbs free energy for this reaction was negative 817.9 kilojoules per mole, divided by, in the denominator is the thermodynamic R, so 0.00831 kilojoules per mole Kelvin. Then also in the denominator is the temperature, the standard temperature, 298 Kelvin. Let's take a quick look at what cancels here. Looks like we got kilojoules and kilojoules canceling. We got moles and moles canceling. And we got Kelvin and Kelvin canceling, which is a wonderful thing. So rounding to 3 sig figs, we get the natural log of K is equal to 330 with a decimal, show 3 sig figs. I can't remember if it's on the next slide or if it's this slide, but in order to do your homework, and if you want to isolate this, if you take both sides, E raised to the ln of K is equal to E raised to the 330th power, okay? This then, over here, E raised to the ln of K, that's equal to K. And so simply, K is equal to E raised to the 330th power. Okay? So E raised to the 330th power is 2.08 times 10 to the 143rd power.
Wow.
No doubt. Would you say it's a little product favored? Big K's means it favors the product. That is one big number, isn't it?
I wouldn't even know what to do with that.
That's bigger than a mole. That's a lot bigger than a mole. So let's take a look at these. Donate to Taco Bell?
No, Africa.
Oh, like, well, that's strange.
Whatever you like, yes.
Man, that'd be in the longest country for quite a few years.
I would never want to run this country, but I'm going to Africa.
Yeah. Cool. So these are for regular credit, both of them. So it mentions you'll be using the appendix or the slides, if you can find them. I bet you can. So basically my hint was to come up with the delta S and the delta H, okay? And then plug into that one relationship that brings them together. Where'd you go? There you are. Then plug into these to get your delta G's, or your single delta G, excuse me. And then go ahead and like in that problem that we just worked, you're trying to solve for K, so my hint over here is to remember that leave it as the ln of K is equal to blah, 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 and then knock out what K is by basically taking E raised to whatever that number is. Kind of like we did in the next one. Looks like this. Again, use the appendix and get to the delta G for that reaction. Once you have delta G, of course you have R and the temperature. It's very similar. What I don't know, quite frankly, maybe you're thinking this too, is why didn't we do 36 like we're doing 37? Why didn't we just look at the, seems easier. And I don't know, I looked at my notes and that's what I did before. So if there's a column for delta G for the previous stuff, I do it this way too. So I want to do just a few slides in the next part. We are going to be in okay shape but I already know that Thursday for lab, we're gonna do balancing, what's scheduled. Lab says Thursday we're gonna do balancing equations by the half redox method.
Yeah.
Okay, so we're gonna do that, but we're also on Thursday gonna have to do a little bit of electrochemistry. Or else. So we just need to. So this will kind of set the stage for tomorrow's lecture.
So we're not gonna finish part 6, like, or this unit before the final, or are we going to?
There will be some at the end of this unit that I'll tell you will not be covered.
Oh, no biggie.
But this will be covered. So, I didn't focus on different reaction types, but there's the ion exchange, or there's the exchange reaction where the cation and anion switch partners. Okay, that's a broad type of reaction. Remember, a chemical reaction by definition is you get new substances are formed on the product side. There's another sort of chemical reaction, and actually to know if what sort of product's gonna be formed, it's called an oxidation reduction reaction. So basically, on the product side, you end up with stuff that has undergone, actually we're going to talk more about it tomorrow on Wednesday. Basically, something is oxidized and something is reduced. If I have a reaction arrow here, something's oxidized and something's reduced. Kind of like conjugate acid-base pairs, but not really, Okay. So we're going to spend some more time Wednesday looking at, it's like you have to take atom by atom in the reactants and products and identify what's called an oxidation number in order to understand the oxidation and reduction that's occurring. So identifying the oxidation number for each atom is important. So this is one way I'm going to take you through. It's basically coming up with what's called the apparent charge at the ionic limit. And it kind of reminds me of the formal charge, but it's different that we looked at in Chem 1. So it basically assumes that atoms that are bonded together, that all the bonds are ionic, which is kind of dumb, right? Okay. So the deal is you are going to look at how electrons are distributed, assuming that the one that's more electronegative gets all of the electrons that are being shared. No electrons are shared, no electrons are spared. Whichever one is actually more electronegative is going to get all of the electrons that were part of it. So this ionic limit is kind of like I said, kind of silly, but it works. So in order for you to remember, who's going to get all the electrons, here's what you're going to have to remember. The one with, do you remember we used the Greek letter chi for electronegativity? That's electronegativity. And we said for the main group elements, so that's group A elements, we said electronegativity increases from left to right, so chi increases. We also said electronegativity increases from the bottom up. And that's just for the group A elements. Because it's going to be important that whoever gets the electrons is the one with the greater, because you take them kind of pairs by pairs. So then all I have is an example, almost. So the assigned oxidation number for a cute little atom is a little fraction problem. Do you guys remember how to get the valence electrons for an element? You look at the group number. So this is from the periodic table. That is the group number from the table, periodic table, P table. Okay? And from that, you have to look at the structure and you subtract the number of valence electrons at this weird ionic limit. Now we have one example. So if we look at carbonyl dichloride. Go figure. We're going to, on the next slide, assign an oxidation number for each atom. But we need to evaluate those two things. Well, I guess there's not much evaluation for the valence electrons. We just use the periodic table. But we need to evaluate electrons at the ionic limits. So here we go. First off, you have to find them on the periodic table. If we pick on this guy right here, this situation, oxygen and carbon, I'm looking at it right now. I told you electronegativity increases from left to right. So do you buy that oxygen's more electronegative? Okay. So that's why here in a minute, that's why you see these, this double bond has 2 electrons and 2 electrons. We have a sigma and a pi bond. That's 4 electrons with a double bond. All 4 electrons go with the oxygen. Why? Because it's more electronegative. Let's pick on these chlorines. Chlorines and carbon, let's see, let's look at the periodic table. Ooh, that's kind of a tough one, but to me,
You split it?
no, they'll never be split using this. That's formal charge. We are not going to split it. Chlorine is going to be more electronegative. It's a little bit confounded, but it does look like it's over there. So if chlorine is more electronegative, then that's why they get both of these electrons. So if you're keeping track, carbon doesn't have anything at the ionic limit. Carbon doesn't have anything because we went oxygen, then we went chlorine. It loses in both cases. So that actually is this number right here. Okay, so we can calculate the formal charge, not formal charge. Sorry, we can calculate the oxidation number by taking carbon's a group 4A. So we take 4 minus 0. 4 is its group number, minus 0 because it doesn't have any.
Didn't we do something like this?
Yeah, but it's formal charge. It's different. I talked to my husband about it. I was like, really? So yeah. Yep. And so we can do for chlorines, or picking on oxygen. Oxygen's a 6A element. And in this particular case, it has 8 electrons at the ionic limit. So, dang. 6 minus 8, it's got an oxidation number of -2. Those chlorines are identical. Chlorine is an 8A element. Sorry, darn it. Chlorine is a 7A element. Okay, in this case, it's got 8 electrons. They both do. So 7 minus 8 electrons is -1.
So does that have to always be like a positive or negative or?
Yeah, I think so. I think to me, you want to emphasize that that is a +4 and put the plus there. So this oxidation number is +4, oxidation number -1, -1, and -2. And actually, it would probably be like this: +4, -2, -1, -1.
So it's always going to equal 0 then?
That's one of the things
Okay.
we're going to talk about on Wednesday. That's right.
Okay.
As long as the thing's neutral, it's going to be neutral. It's going to be equal to 0. All right, very good. Thanks for staying a little bit longer.
Oh, I know I should know this, but isn't the density